Chapter 4, slides 28 to 55. This chapter specifically now is going to look at the conformational analysis for rings. Now, rings are really important in chemistry in general. So far, we've been looking at alkanes as chains mostly, and it's important to understand that because of the conformations that we see, right, molecules are not stagnant things. They're moving, they're rotating, they're fluxing. And so if you have a specific job for a molecule, let's say you're thinking about a drug, and that drug needs to interact in an enzyme pocket, and it has to fit in there just so. You need to have some rigidity to the molecule, right? If the molecule is rotating, if you have a long, flimsy chain, right, and it's rotating, and it could have lots of different orientations, then it's flimsy, like a piece of spaghetti, and it can orient in lots of different shapes. And that's not good because it might fit into every single enzyme pocket under the sun and without specificity, and it could do a lot of damage. When you need specificity for a material or for a pharmaceutical candidate, you need to design the structure of it so that it stays somewhat rigid. One way to implement some rigidity is by using rings. Rings tend to limit free rotation of bonds, as we'll see, and therefore give some stability, some rigidity to the molecule so that it maintains some type of shape. Not that it's always in one set conformation, but it is limited. The number of free rotations is brought way down. So rings are prevalent in nature, in pharmaceuticals and materials because of lending rigidity. So let's take a look at cycloalkanes. The carbon atoms in the rings below are what? What's the hybridization of each carbon atom for the compounds below? If you said sp3, you are correct. So let's bring back our chapter 1 stuff. What's the bond angle, the optimal bond angle for an sp3 hybridization? If you thought, well, tetrahedral is the shape, and 109 degrees approximately is that bond angle, you were correct. Okay, so now let's bring back our high school geometry. If I were to have a 3-membered ring, cyclopropane, okay, so we're going to look at cyclopropane. In order to make a triangle, right, cyclopropane, the inner bond angle as shown has to be 60 degrees. But the carbon is sp3 hybridized and thus wants to be 109. Ugh, that's not good because you're squeezing that bond really acutely, bringing closer together those two bonds, which are made up of electrons, which repel one another. So this is not good. As I move to cyclobutane, 4-membered ring, it gets a little bit better. Still not great though. A 4-membered ring is a square. You've got a 90-degree angle. Every carbon wants 109, so you're really straining the angle, the ring, to form that, right? You're really trying to pull it out of its normal feel-good hybridization. It's still sp3 hybridized, it's just not happy. Once you get to cyclopentane, the bond angle is now 108 degrees. Wow, that is so much better, right? So what you're seeing is that as we move along, and these are flat paper geometries for these shapes. This is what you learned in high school. As we grow the ring number, the angle becomes a lot better for the molecule until it doesn't, until you get to an angle that's so large that now we have an opposite problem. It's too obtuse. Okay. So in order to optimize bond angles and not have something called angle strain, most cycloalkanes are not going to be flat like we draw them on paper. And that's not going to be the most stable conformation for them. So Why does it make a molecule less stable to have angles less than 109.5 degrees? Well, as we mentioned, the answer here is electron repulsion. If we bring those bonds, which are made up of electrons, closer together, we have electron-electron repulsion. So we don't want the angles to be too far outside the normal hybridization for that carbon. Okay, so that's bad. That would be called angle strain. We also don't want the angles to be larger or greater than 109.5 degrees, because the larger the angle becomes inside, the smaller the angle between the other two becomes. And again, you're just getting electron-electron repulsion, which isn't good. So this is called angle strain. Okay, angle strain is one of the things that is responsible for something called ring strain. So there are two parts to ring strain. The easiest one to see is the angle strain we just talked about. So it's a combination of angle strain, and that's due to the fact that we know what the hybridization is, we know what the perfect bond angles are for those hybridizations. And if we look at angle strain and we also consider what we just took away in the previous slides, torsional strain, we'll know something about ring strain. So ring strain is an umbrella, and it encompasses both angle strain and torsional strain, two different types of strain that we consider when we look at ring strain. Okay, so it's a two-component system. Let's start with cyclopropane. If you look at cyclopropane, you can even tell from my models that the bonds, the sigma bonds, they're not happy. You can even see them, they're kind of bowing. Even in my model system, they're bowing, right? And what you'll notice is that there's no way, it's such a rigid molecule that there's just no way to twist it and turn it. And no matter what we do, we can't twist it to a staggered conformation. If you look down any two carbon atoms in the system, try to put it into a Newman projection, every single hydrogen off of the carbons are always going to be eclipsed. There's no way to rotate it out of its eclipsed state. So cyclopropanes have a lot of ring strain. Why? Because they have very acute angles. They're much smaller than the required or desired 109 degrees for the hybridization of sp3. And you can't get it out of eclipsing the hydrogen bonds off of the carbon. What if we looked at cyclobutane? Now, the interesting thing about cyclobutane, unlike cyclopropane in the previous slide, is that cyclobutane is not flat. It's actually bent a little bit, like you can see down here at the bottom. And so what that does for us is that it pulls a little bit those hydrogens to not be so eclipsed to one another, just a little bit. It has a little bit less angle strain than cyclopropane, right? It's not 60 degrees, but it does have the potential for 8 eclipsing hydrogens compared to the cyclopropane 6, but it relieves that by bending a little bit. It's got a little bit of bend in it, and that relieves a little bit of the torsional strain. So you can see that you still have eclipsing, but you can get a few of them just slightly not eclipsing. Okay, let's go one more, cyclopentane. Now, cyclopentane has very, very little angle strain. As I showed you, its angles were 108 degrees, very close to the desired 109. That's great, right? But if we draw it flat, everything's going to be eclipsing. So the shape, the conformation that cycloalkanes like cyclopentane take is called the envelope. And the reason why is because one of its carbons will kink drastically up, with the remaining 4 being pretty much planar to one another. So these 4 carbons are kind of planar to one another, but one of the carbons kinks up like an envelope, and that relieves a lot of the torsional strain. Not all of it, but it relieves some of that torsional or eclipsing strain by the bonds off of the hydrogens, or off of the carbons. It's not perfect though. So the cyclopentane does have some ring strain due to torsional strain, not so much because of the angle strain. This brings us to cyclohexane, which is like the magic perfect number of carbons to make a ring where everything just seems to be so stable. It's one of the reasons why, if you've ever wondered why 6-membered rings are so prevalent in nature, in pharmaceuticals, in materials, and so much, it's because of the low energy we can obtain through the conformational structures of cyclohexane. Cyclohexane pretty much has 0 ring strain. 0, right? And you might go, wait a minute. Back on that slide, you showed me the geometry of a 6-membered ring has an angle of 120. Doesn't it have some angle strain? Okay, well, that was geometry on paper. That's a flat cyclohexane. Cyclohexane, though, is not flat. And it can assume many different conformations, but one in particular that is the most important, it's called the chair. There's another one, there's actually quite a few. Let me go to this slide and show you there's quite a few. There's the chair, and you can see that it's much lower in energy, right? And then if you just pull one of the sides up, you're in a half chair. It's almost like the envelope version of the cyclohexane. And then you bring you bring that end all the way up, and now when you have both tips, so it's like you have 2 parts of the envelope, both are kinked in the same direction, then it's called the boat. And you'll notice that the boat is a conformation that is not as bad as the half chair. There is something called a twist boat, which is a little bit lower in energy, but we're not going to concern ourselves with those. It goes through another half chair on the other side, back to the other chair conformation farthest to the right. We're going to be focusing on the chair conformations. And I say conformations because if you look, these 2 conformations have different ends up and down. So what I want you to get from this is that there are other conformations of a cyclohexane, but there is a drastic energy difference in conformations. And so the ones that are the most prevalent that we are going to use in this course are called chair conformations. And as I mentioned, cyclohexane is considered to have pretty much 0 ring strain. And why is that? I mean, doesn't it have a little bit of angle strain? Well, no. Because we've kinked the ends of the carbons out of the plane, it actually changes the angle quite a bit. And you can even feel it. If you have a handheld model and you try to make all carbons for your sp3 carbons planar, you'll see that the bonds will be bending and straining. But once you sort of shake the molecule, you'll see that it'll naturally go into a chair conformation because all of the bond angles will be 109.5 degrees. So when you have a chair conformation, the key here is that you're allowing those angles to be exactly 109 degrees. So no angle strain. Okay, now let's see about torsional strain. Let's use our Newman projections. What if I took my eyes and I looked down the carbon here and at the same time looked down the carbon here to the back of those carbons? So that means the carbon and the carbon, carbon 1 and carbon 2, carbon 1 and carbon 2. If you look down those carbons, you'll see that there's a carbon in the middle. So the carbon in the middle of your vision dips down, and you can see that the carbon behind in the back that dips up is this one that you're seeing in the back. It's another perspective. Again, the chair, okay, which is how we're going to draw it the most, the sidelong view, the side of the barn view. Lucky for you, side of the barn view of a cyclohexane is how we're going to show it because it's just a little easier to see. This is the Newman projection for a chair of a cyclohexane ring. Now, in drawing the Newman projection, what it's showing you, and I can show it to you in a model as well, is that every carbon you look down, I could have turned this in any trajectory. This Newman projection is always going to show each carbon on either side as fully staggered. Every carbon-carbon bond association with all of its hydrogens or whatever substituents are off of the cyclohexane will be staggered. So the chair allows for 0 ring strain because no angles are outside of 109 degrees, and all of the bonds off of the 6 carbons in the ring are staggered at all times to one another. That is what makes 6-membered rings so prevalent in nature and in construction. If they're that stable, they're much easier to make. And it's why we see it so much in nature. Why is this called the chair? Well, I think some say it resembles a recliner. Some say, I mean, you could even look at conformation of us, right? When I showed you that picture of a person standing up and a person sitting down, you can kind of see the sitting down has that chair kind of conformation to it. The boat conformer doesn't have any ring strain, but if I do a Newman projection of that boat conformer, which we saw before is higher in energy, you'll see that the conformational analysis, right, with those 2 carbons, the forward carbon, the back carbon, they're both up. They're like on top of each other. And the 2 carbons we're looking at in the Newman projection are shown here because my eye is, again, looking at this molecule from the barn door side, not from the side of the barn. I'm kind of going around perspective-wise and looking at it from the other angle. And then you can see that everything is pretty much eclipsing one another. So although we don't have angle strain for the boat conformation, what gives it the higher energy is the torsional strain. What I want to spend our time talking about is cyclohexane conformers, specifically the chair. I want you to learn how to draw them because they're kind of hard to draw. Make sure that we're looking at it from the same perspective, and then identify positions on the cyclohexane chair as either axial or equatorial. Let's begin by learning to draw the cyclohexane chair. What I like to do, I don't know why, I always relate it to a duck. So I draw a duck beak. There's my duck. I don't know. So I'm going to draw a little duck in the corner so you can see. Here's my duck. And then he's got a tail, right? Maybe I can draw a bigger tail. There's his tail. He's got feet. Okay, so there's my duck, not an artist. And I start with the duck beak. All right, here's my duck beak. And then I'm going to draw 2 parallel lines, the front one being longer than the back. And then I'm going to draw his tail. Okay, so if my duck is looking, you can say is looking down, right? Here's his eyes. He's kind of looking down. And my duck is left justified, so my beak is on the left, my tail is on the right. If I keep beak on the left, tail on the right, I can draw the other chair conformation very easily by now making my duck point up. So my duck is now looking up and his tail has gone down. So these are the two chair conformations. And the first thing I need you to do is, when you're in another class and you're bored because it's not organic chemistry, right? Doodle on a piece of paper. Just practice. I used to just practice drawing my 6-membered rings. I always drew one better than the other. There's always going to be one of these. I think the one where my duck is looking down always looks better. But you can like practice drawing them. There's your chair. It just takes a little bit. All right, just keep practicing both conformers. You need to be able to draw both. Oof, that was a bad one. See, I should sit in classes that bore me and practice drawing my cycloalkanes. There you go. So there, just keep doodling and practicing, okay? It takes some practice. Now, the perspective that you need is to understand that the bottom of the ring because this is a 3-dimensional drawing, okay? This is not a flat structure. This is a 3D drawing. And to give it some perspective, I'm going to shade the bottom of the ring. So the bottom of the ring is closer to us. So it might be like one of those images where you might not see it until maybe I shade it. So like this edge, maybe that gives it some perspective, is more coming at us. So you can see that there's a group that we're drawing in the back there that's behind, right? It's in the back. And so you go through, you basically, if I was going to draw something on this back carbon, because again, this front edge, this bottom edge is more towards us. Trying to erase my blue here. Okay, so that bottom edge is coming towards us. And so if I were to, that back carbon, if I had a hydrogen going down, notice how I split the bond to give it that 3-dimensional look, right? So I just want you to be aware of that. In the front here, this carbon that I'm highlighting, if I had a hydrogen going straight up, I wouldn't break the bond because it's in the front. So perspective-wise, it's more on my side, okay? It takes a while to get these, so be patient with yourself. Now, what I want to highlight next is all of these positions off of the cyclohexane ring. Now, I've done this with blue circles and pink triangles, but for each carbon of the cyclohexane, it's sp3 hybridized and has 4 bonds. 2 of the bonds are to other carbons in the ring. That leaves 2 other bonds to be going off of it outside, right? The circle and the rectangle. I want you to focus first on the triangles. Focus first on the triangles. I'm going to start in the bottom left. All of these are called axial. Think about the Earth on its axis. Right? You've got the Earth, and you've got the North Pole and the South Pole, and that is the axis that the Earth spins around, right? The up and the down, the north and the south, the up and the down. So this is an axial position. It's straight down. This is also an axial position. It's straight up. I'm going to put down in parentheses there. Okay, so what you'll notice is that every single carbon around the cyclohexane has an up axial, or has an axial up, and then it alternates axial down. So if I start with the yellow one, axial down, the next one over is axial up. The next one over in the back is axial down. The next one's axial up. The next one's axial down. The last one's axial up. So it's alternating. Why? Remember that in a Newman projection, one carbon has some group, and in the back, the best method of orienting these groups in a staggered conformation, if you can put those groups opposite or anti to one another, you've oriented it in a staggered conformation with the two groups anti to one another. So axial up and axial down, if you look down the barrel of the carbon-carbon bond, you'll notice that they're the ones that I've highlighted, the axial up and axial down, they are anti-staggered to one another. So the first thing I want you to do is to, when you draw your cyclohexane, go on each carbon and draw an axial up and an axial down. And I think it's easier to start with the axials so you don't get confused. If your duck is pointing down, you can kind of see that you'll start with an axial down. So this is an axial position. Axial. 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 Okay, I can do the same over on the other side. Axial. 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 Axial, axial, just make sure you're alternating them, axial. Okay, it's up or down, but they're all axial. So pay attention. Notice that axial can be up or axial can be down. There's a north face to this molecule and there's a south face to this molecule. Next, we're going to draw the equatorial positions, and I want to make sure that things are staggered. So if I start with the carbon, equatorial is going to be, I want to form a triangle, right? Form that tetrahedral shape. In the back, I don't want to put the hydrogen eclipsing, so it kind of bends down a little bit. In the back, it bends up, bends down, bends up, bends down. Again, try not to eclipse the hydrogens. Don't draw the two hydrogens like this. They look like they're eclipsing one another. So if one of them is, if you're angling it a little bit down, angle the other one up so that you can see that they're askew. This takes practice. So be patient with yourself and understand that cyclohexanes have two conformations. They have, at every carbon off of that cyclohexane, they have an axial position and an equatorial position. I could have changed all of these H's to E's. E for equatorial. Okay? Do not draw any equatorials going towards the inside of the ring. Always draw them on the equator, right? So here's your equator. They're all going to be coming off of the end, around the equator, okay? Do not draw them going towards the middle of the, or through the cyclohexane. So practice, 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 practice. Now I had drawn an equilibrium arrow between these. Why? Because these, through bending and rotating, can change from one chair to another. Chair 1 to chair 2. Okay, so we'll call this one chair 1 and this one chair 2. Chair 1 and chair 2, if there was all hydrogens around, there would be no difference in energy between either conformation. Okay, and so these can, just by bending and rotating, convert from one chair conformation, bend, 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 convert to the other chair conformation. Okay, bend, bend, bend back, and they're in equilibrium. Sometimes, though, the energy between them is different, and one chair may be preferred over another. This is called ring flipping, and unfortunately, it doesn't mean flipping like a pancake. It means doing exactly what I showed you with the model, twisting and bending to convert it from one chair to the other. Duck beak up, duck beak down. You're not changing the direction. The duck is not changing its direction and flipping over. It's just literally bending and rotating, looking down, looking up, looking down, looking up. Okay? So it's rotational. What's interesting about a rotational flip, if you will, is what happens to the things off of any given carbon. So let's look at this carbon 4. We've arbitrarily numbered them. So carbon 4 has an equatorial group off of it. Let's say that it was a bromine. Okay, equatorial bromine. And it has an axial hydrogen. When you ring flip this, that means the duck beak flips up, right? It flips up. So now your duck beak is here. Look at carbon 4. Notice that the bromine is now in the axial position and the hydrogen is now in the equatorial position. So the hydrogen was axial and down relative to the bromine. After the flip on the same carbon, the hydrogen is now equatorial and down relative to the bromine. So the key here is that when you do a ring flip, when there's a conformational switch from one chair to the other, all of the groups change from equatorial to axial and axial to equatorial. So conformational flip changes equatorial to axial and axial to equatorial. Those are not set in stone. One of them is going to be preferred over the other. And we'll talk a little bit about this later, but I'll give it to you now. When you have all of the groups axial, let's say that there was a hydrogen here and a hydrogen here. The larger the group, the more interaction it has with the other nitrogen, or so the other groups, in this case hydrogens, on that north face. So these are axial interactions. And the bigger the group, the bigger the interaction. And when I say axial interactions, we're talking more like steric hindrance. The bigger, the bulkier the group, the more they bump into each other. When you're on the equator, right, around the edges and pointing outwards, you have much less steric hindrance. And so it's really only when you're down axial, bumping into stuff on the south face, or up axial, bumping into things on the top face. So if I were to draw an equilibrium between these, I would suspect, since bromine's the biggest substituent off of the ring, I would prefer to have the bromine out in the equator. Equatorial is lower in energy than axial for the bigger groups. And we're going to see that seen quantitatively in a subsequent slide. One of the things that I liken this to, again, I go back to my duck analogy or my bird analogy. It's like having a feather on the duck's head. Okay? And the duck always has a feather on its head. So what I also want you to notice is that the position always changed, right? Equatorial became axial and axial became equatorial. But did you notice that the group itself, the up nature of it or the down nature of it, never changed? So axial was, hydrogen was axial down in the beginning, and it switched to equatorial down. Bromine was equatorial up relative to the other group on the carbon. It's up relative to the hydrogen, and then it switched to axial up. But notice up stays up and down stays down. That's going to be very important, especially when we look at chapter 5. So up stays up and down stays down. It's only the equatorial and axial conformations that change. Being up, being where you are relative to something else, is not going to change. You'd actually have to break bonds to change their relationship to one another. And so I highlight this in this image. If there was that, here's your bromine. Okay, I'll say that's your bromine. This is your axial up. And then your duck, so this is one conformation of your duck, and it just so happens that the group that you're interested in is like a rogue feather on the duck's head, and it's sticking straight up in the axial direction. Okay, the duck twists and conforms and bends and forms the other conformation of itself as it's eating. The feather is still up on the duck's head, so its position up and down is not going to change. It's still up on its head, but now it's up and equatorial. And it literally just did this by bending and twisting its bonds at the hip, bending over and giving it more of an equatorial position. So let's go back and look at lower energy conformations. I hinted at this with the bromine example. So if you have, now you know how to draw cyclohexanes, and you have the ability to draw a substituent off of one of those carbons, I want you to be able to draw both chair conformations with that relative substituent. Let's say we had a cyclohexane with a methyl on it. Another way to write a methyl is CH3. That's a nice, tetrahedral ball of electron cloud density. You would have an axial conformation, and then I can draw the hydrogen that's equatorial just to kind of keep things in perspective. And you can see the tail is up, and now the tail is down. The methyl has to be at the tip of the tail every time, and so that methyl, that CH3, still up relative to the hydrogen, but it went from axial to equatorial. And what you'll notice is that the equatorial dominates in the equilibrium. Why? The answer here is steric hindrance. In the other geometry, when it's axial, it's going to bump into the other axial groups on the north face. In this case, again, the north face of the molecule on the axis, on the north axis. And in the equator, it's sort of out and away from all the other stuff, so it's farther away. So the hydrogens of the methyl group have steric hindrance with the axial hydrogens. And I've showed this steric hindrance sign to you before. And in ASL, we do something like this to represent the banging of the electron clouds, right? It's like these two clouds are just getting too close to each other and they're repelling, and it's called steric hindrance. More specifically, for cyclohexanes, we actually call this a 1,3 diaxial interaction. Some people could just say, oh, it's all the axial positions being sterically hindered, right? Bumping, those electron clouds bumping into each other. But it has a very specific, the steric hindrance in this particular case has a specific name. And it's because of the 1, 2, 3, 1, 2, you can't see it, 3. Maybe I can number it here. 1, 2, 3. 1, 2, 3. If you'll notice, it's a 1,3. The positioning of the carbons in the ring are a 1,3 diaxial interaction, and it's bad, right? They're bumping into each other. We want to minimize that. We want to minimize steric hindrance. So we've ring flipped to get the largest groups in the equatorial positions. The larger that group, X, the greater the energy due to steric hindrance. And you can see that as we go through. As we switch from, say, an OH to something more tetrahedral with bonds coming off of it, CH3, put more carbons off of it, ethyl, isopropyl. So if I had an axial methyl. That's going to interact with the two hydrogens in a bad way. But what if I made the ethyl into an isopropyl group? Whew. What if I made the methyl or the isopropyl group into a T-butyl group? Oh my God, that's a huge, huge group. That is not good. Look at the jump it makes from isopropyl to the T-butyl. That is a huge jump in kilojoules per mole. So you really got to get those. Look at the equatorial. So this is the equatorial to axial ratio. When you have a T-butyl group, you're never going to see this T-butyl group axial. It's always going to be in the chair conformation that allows it to be equatorial. You know, and you can see that there's a little bit more when you have say a chlorine, which is a lot smaller, more of a 70 to 30 ratio. So it's dependent. You're not responsible for these numbers, but they're interesting, and you can find them in strains for cyclohexane rings. Now I want to add one more thing to you practicing drawing these cyclohexanes and finding their low energy conformations. If you have stereochemistry, which is what we're going to talk about in chapter 5, but let's use it relative to what I alluded to earlier in the chapter, cis-trans isomers for these types of molecules. As I showed with that cyclopropane, you could have the two groups cis or the two groups trans to one another. So if I have two groups, okay, and they're given wedges and hashes, I want you to equate a hash as meaning down, right? So we've looked at hashes as meaning back, and I want you to just expand that as that hashes mean down. It'll help you when you're trying to draw a cyclopropane or cyclohexane ring. When you have a wedge, I want that to mean up or towards you. Okay? So that means when you're drawing cis 1,4-dimethyl cyclohexane, and they've drawn cis as shown, I'm going to number 1, 2, 3, and 4. Try to keep things the same. 1, 2, 3, and 4. So the carbons at 1 and 4 are the ones that have the substituents on it. And if you'll notice, both of them are hashed. So drawing my axials first, I know that I have an axial down, and since I see the CH3 is hashed, I know I've got to put the CH3 at that down position. So the hydrogen must be up. If you go all the way over to carbon 4, that CH3 is also down, and down is the equatorial one in this case. That means the hydrogen must be up. So what I want you to understand is that the hashed and the wedge mean up and down. They have no correlation to equatorial or axial, because I'm going to draw the ring flip now. One, two, three, 4. I draw my axial and methyl trajectory. Up is up and down is down, so methyl has to stay down. Notice that at carbon 1 had a methyl down but axial. In the ring flip, carbon 1 has a methyl down, still down is down, but it's equatorial. I successfully ring flipped. Look at the beak. The beak is down with the methyl down. The beak is up, still with the methyl down, but it just changed the orientation from axial to equatorial. You can do the same on the tail end. Methyl started equatorial down. Down is down. I got to make sure I keep it down because it's a hash line. So therefore the hydrogen's up, and I successfully switched from equatorial to axial. Equatorial and axial switched, but down stayed down. These are the two conformations for the cis isomer. What you'll notice is that in one, you have an axial methyl and an equatorial methyl. And in the other, you have an axial methyl and an equatorial methyl. So I'm going to keep the equilibrium as 50-50 because one is neither better than the other. Let's do the cyclohexane for trans. 1, 4. Now look, we've got a wedge. That means that the CH3 is up. So I have to put the CH3 over here in the up equatorial position. So the hydrogen must be on the other side. When I go to carbon 4 on the other end, I have an axial and an equatorial. Just got to make sure you drew them in the correct trajectories. And I see that the bond is hashed. So the CH3 is down. It's equatorial and down. That means the hydrogen must be on the other position. So I've got my tail. I've got my beak. And I need to draw the other conformation. Both pointy ends. Now I've ring flipped. Be sure to draw the trajectory of your system correctly. Up stays up, so CH3 has to stay up, but it did indeed switch from equatorial to axial. The hydrogen must have been on the equatorial then. And for the other side, the methyl is down, so down stays down, but it switched from equatorial to axial. Success. Okay, now when I look at the trans conformation, I can see that in one conformer, both methyls are equatorial, and in the other one, both methyls are axial. Due to steric hindrance, due to the 1,3 diaxial interactions, both on the south and on the north face, there are 1,3 diaxial interactions below. There are 1,3 diaxial interactions above. I know that the equilibrium arrows are going to favor the equatorial, and I would draw them like so. Why is this interesting and important to learn? Well, when you know what conformation a molecule resides in most of the time, it's like having a person in a room. If you know that their lowest energy conformation is sitting down on the couch, then as a mom, 90% of the time that I walk by the door and peek into the living room, let's say 90+% of the time my kid is sitting on the couch. That's because it's their lowest energy conformation, right? There's a very slim possibility that I walk by the living room, peek my head in at any given instance and see that they're doing push-ups, right? Highly unlikely. That's a much higher energy conformation for them. And so if you know that the molecule exists in that conformation, I don't know, 90, 95% of the time, then you know that when you're going to react the molecule, that's most likely how it's going to be, and it's going to lead you to one product maybe more than another because of its spatial orientation. So having an idea about the lowest energy conformation of a molecule, because they move around, knowing how it is most of the time is actually very insightful when you're trying to make guesses and hypotheses about the major product of a reaction. So you're going to have to get comfortable converting what I call these 2D structures, right? Because we're going to draw them this way. They're very easy to draw. But you've got to understand that they're not a good representation of the 3D chair drawing. Okay? So in a 2D structure, in order to give some sort of hint about the three-dimensional nature, we have to use the wedges and the hashes. Okay? What I don't want you to do, I don't want to see this. Okay? That is absolutely wrong. You do not use wedges and hashes on what's already a three-dimensional representation, right? Remember this front edge, I'm okay if you like darken it a little bit to give it some perspective, but these are 3D drawings, and they shouldn't have wedges and hashes. The wedges and hashes are reserved for when we draw very, flat, planar looking molecules. We need those wedges and those hashes to indicate some three-dimensional tetrahedral nature. So here again, you can see two chair conformations for the same molecule, and you could try and figure out which conformation you think would be more stable. First, you'd have to decide which group is bulkier, and I would say methyl is, and you could go back to that table and see that chlorine's energy for steric hindrance versus a methyl's energy for steric hindrance, there's a big difference. So if you could look up quantitative numbers for these diaxial interactions in kilojoules per mole, or you could see this is like a tetrahedral cloud while this is one atom and it's on the small side. So I want that methyl group, which is the bigger one of the two, to be equatorial. And what's nice is that putting it equatorial also happens to put the chlorine equatorial. So I didn't even have to split hairs and decide which group was going to be more important. What you can do now is label the chlorine and the hydrogens on each of the chair conformations as up or down. And you can see the chlorine here is up. It should stay up in both conformations. Same thing with the methyl. The methyl is down. It should stay down in both conformations. Up is up, down is down. Only axial and equatorial change positions when you are going from one chair conformation to another. Polycyclic systems having more than one chair, we can see these from time to time. I'm not going to ask you to draw them, but just be aware that you can start fusing these and making bicyclosystems in chair conformation, because if you really think about sheets of carbon in six-membered ring, six-membered ring, six-membered ring, all fused together, they're going to either form cis-decalin or trans-decalin type systems, and you can see the trans-decalin is probably more lower in energy and more stable because the hydrogens are anti to one another. This one has a little bit more steric hindrance with this carbon is axial down and has some steric hindrance, so cis-decalin's not as good. So this trans-decalin sort of format, fusing all these chairs together in 3 dimensions, is actually how diamonds are formed in all arrays and directions. That's how the carbon array is for a diamond. We'll also see a lot of these 6-membered rings in materials and pharmaceuticals. One nice party trick is being able to look at a molecule and go, oh, that's a steroid. You can wow your friends. If you go to your own medicine cabinet, if you are on a steroid yourself, a steroid cream for maybe some skin problems, or maybe you have asthma, look at the white piece of paper that's folded a bajillion times that comes with your drug and open it up and take a look at the molecule. If it's a steroid, you're going to see a 6, 6, 6, 5 fused system. That is the trend for all steroids, both, natural to our bodies that we biologically make and the ones that we synthetically make for the purposes of pharmaceuticals. So here's a list of your critical skills and retrieval cues from this chapter. This is a doozy, and it's a very 3-dimensional chapter. So make sure that you have got those critical skills mastered at the end of chapter 4. Now, just to make light of things, if you ever talk to any students who have taken organic chemistry, these are things you'll hear from them. All the things that you learned from organic chemistry, mostly you're going to learn how to draw hexagons really well. And I'd say, please learn to draw a chair. I also like this, since we were just talking about nomenclature, I saw this joke where someone said, what is the name of this molecule? And they wrote something like 1,2-dimethyl chicken wire or 1,2-dimethyl honeycomb, which, definitely says it all. I leave you at the end of this chapter with an onslaught of practice, practice, practice. Okay, this gets you to distinguish between cis and trans by looking at chairs and maybe converting them to their 2D structure using wedges and hashes, and then deciding if it's a cis relationship or a trans relationship. Practice drawing both conformers for the molecule shown, and then tell me which one the lower energy is. Do the same for this one. Do the same for this one. And again for this one. Here's a little bit more nomenclature practice. Here I show you the molecule and you name it. In the second one, I name the molecule and you draw it. This is an example where I told you it can be very tricky sometimes trying to wrap your head around the fact that, is this the same molecule just kind of twisted, right? It's hard to tell sometimes. So I want to know if these molecules are the same, or are they constitutional isomers, right? So how can you do that very quickly? I told you earlier in chapter 4, you could just name both of them. So it's good naming practice. And if you follow the IUPAC system, if they truly are the same molecule, even though they look different, you should end up naming them the same if they are the same. If they're different, they'll have two completely unique IUPAC names. Here's a little practice with a Newman projection that's a bit tougher to analyze. Maybe try to redraw it not in a Newman projection and see if you can give the name of it. So name the molecule, draw its bond line structure not in a Newman projection. And you could also see, is this the lowest energy Newman projection for it? Here's another doozy. Draw the highest and lowest energy chair conformations for the molecule. And by this point, you'll have done a lot. This combined with your homework problems and any more chapter problems, extra practice problems from the textbook, you've really got to hone these skills. You will use them. So good luck.